All right, so let's get going. Couple quick announcements before we get started. So, as a reminder, we have both the 5.5 mini quiz, it's due tomorrow, but also tomorrow is our chapter 5 quiz. And so, again, with the chapter quizzes, you need to find a 1 hour period to take it. I highly recommend that you take the mini quiz before you take the chapter quiz. Um, and at that point, all of your sort of required assessments will be completed in Moodle after you do those things. Our last homework is due on Friday at 11 p.m. And if you're planning on doing any of the past homework for partial credit, that will also be due Friday at 11 p.m. And so what'll happen is over the weekend, we will process your homework grades and get those posted in Moodle so you can see what your current grade is by Sunday at noon to make a decision about whether or not you want to take the optional final on Monday. So again, the final is completely optional. You don't have to take it if you don't want to. And what that will do is if you do take the optional final, it will replace your lowest chapter quiz grade. And it is set up so that the higher grade is taken. So if you do worse on the optional final, you won't be penalized. So again, it's completely optional. It goes towards chapter quizzes, which have the highest impact on your overall grade. And it's up to you whether or not to take it. If you want to take it, you simply log into Moodle during our scheduled final exam period, which is 10:30 to 12:30. You'll have an hour to take it, so you can start at any time in there by 11:30. And it's cumulative, and it's 10 questions, multiple choice, just like our regular chapter quizzes. So that's what we have left. There is drop-in help still today and tomorrow. And after that, we don't have any more drop-in help because we don't have any more assessments and the TAs are studying for their finals. So if you have last minute things you're working on homework that you still have questions on, make sure you stop in either today or tomorrow to work those out. Okay, so I think those are the only announcements. William did a review on the chapter 5 review. I posted the lecture link on Moodle. So if you work through the review and you want to watch that session, it's there. Yeah, I think that's everything. So let's jump over to the notes and just get started on 5.5. So, okay, we're gonna switch over to the notes here. I'm just gonna turn off my video of my face because I think it helps the bandwidth, but I'm still here. Okay, so the last section that we're gonna cover, 5.5, is called Total Change and the Fundamental Theorem of Calculus. So as you can imagine, it's pretty important, right? It's called the fundamental theorem of calculus. And there's actually different parts to this theorem, and we only sort of cover the main part. But one of the reasons why it's so important is because this is the theorem that sort of bridges Calculus 1 into Calculus 2. And so I will talk a little bit about what you can expect to see at the beginning of Math 128 if you want to take that and how this is applicable. But most of the focus today will be on what we need to do, which is still talking about area under the curve. Okay, so the theorem says if f prime of x is a continuous function on an interval a to b, then the area under the curve of f prime of x between a and b is equal to f of b minus f of a. And so I want to talk about what this means, what notation we need to look out for, and what this is telling us. So again, the f prime of x, right, that part is representing the area under the curve. Okay, so this is area under the curve. And that's what we've been working on in the past several sections, right? How do we calculate that area? How do we approximate that area? All that sort of stuff. And so that's the notation we've been using. And we know what that tells us is how much the original function changes between a and b, right? It doesn't tell us the value of the function. It tells us how much the original function changes. So what this is saying is the area under the curve, right, which is how much the original function changes, is the same as if we had the original function. So notice this is not the derivative. And we looked at the change between the same 2 points. Okay, so let's think of an example. So we talked a lot about velocity and driving. Okay, so if we integrated from 2 to 5, some velocity, and we found out that the area under that curve was 100 miles, say. Okay, so maybe we had it under a graph, maybe we did it in a table. What this theorem is saying is if we had the position function, which is the original function and how we get the derivative here at 5, and we had the position at time 2, we could also look at the difference in positions between time 2 and 5, and the difference between those positions would be 100 miles. Now, this might either be confusing to you or seem incredibly obvious, okay? Either way, here's what's important. The reason we are not using the original function to see how much it changed is because we don't have the original function, right? The whole premise of chapter 5 is what if we only have information about the derivative, right? If we had the original function and we wanted to know how much the original function changes, we can just plug in two values and subtract them, okay? But we didn't have that. We only had this. We only had the derivative and the area under the curve. And so the reason why this is called the fundamental theorem of calculus is because the first things that you will be doing if you go on to take Calculus 2 or Math 128 is what's called antiderivatives. So that says if we have the derivative in an algebraic form, what do we have to do to go back to the original, right? So all those rules that we learned about derivatives, we would learn a rule for an antiderivative. So this is how we would get this side of the equation. So this is sort of the bridge that ties it. And so this is what we've been doing in Math 127, right, at the end of chapter 5. And finding the original function is how you start Calc 2. And for UMass, that would be Math 128. So this is sort of the first inkling in our side of the bridge. Like I said, if you go on to take Calc 2, you'll learn about this side of the bridge. If you don't, you can either look it up if you're really interested or just sort of be happy with this method of talking about total change. Okay, so now that we have this idea, we're going to use this theorem from our side of the bridge. We're still going to work with derivatives and see what it can tell us and see if it can tell us anything about this side of the equation. Okay, so suppose that ice is forming on a pond at a rate of dy dt equals the square root of t over 2 inches per hour. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, estimate the thickness of the ice after 5 hours. Okay, so we need to think about how we can use the fundamental theorem in conjunction with this problem to solve for the thickness of the ice after 5 hours. So there's several things that are happening here that are important and directly related to what we're talking about and sort of tangentially related. The first, let's talk about the variables we're using here, okay? dy dt. So dy dt is the derivative of y with respect to t. That means that our original function was y, okay? And it says if y represents the thickness of the ice. So that means that the original function was y of t, and what we have is the derivative of that. Well, we can figure out how much the ice changes over 5 hours using what we know about area under the curve. So if we were to set up an integral from 0 to 5 of our rate, which is square root of t over 2 dt, we know that that's going to equal the thickness of the ice at time 5 minus the thickness of the ice at time 0. So this is the fundamental theorem, right? So how do we use this to answer our question? Well, what this question is asking us to solve for is the thickness of the ice at time 5, okay? So what does that mean? That means we want to find how much the thickness changes, right? Which is what we've been working on. We can plug this into our calculator to get the exact area under the curve. And then we have to consider the initial thickness of the ice. So we've sort of talked about initial values before, but now we're going to do this more formally. So the first step would be to plug this into our calculator to get a value, okay? And if we plug this in, we are going to get 3.726. Okay, so that's how much the thickness changes from time 0 to time 5 by 3.726 inches. Then we come over here to y of 0. So how thick was it when we started forming? So the idea of starting to form ice means that at time equals 0 is exactly when you have 0 inches, right? It's just starting to form. It's fluid until the next possible moment. So y of 0, we can argue, is 0, okay? Because think about ice and forming and what will be happening right at the beginning. And so we would add this 0 over, right? Because if it wasn't 0, we'd have to add that number over. And we get y of 5, which is the thickness of the ice after 5 hours, is going to be 0 plus 3.726 inches. Okay. So when we're talking about setting up the fundamental theorem, we are integrating the rate, setting up the original function, right, with our bounds. And then if this has a value, we're going to add it over to the other side to get this value. Or if we wanted this value, right, we would algebraically solve for the other value. So that's sort of the approach we're taking here. We're more formally introducing things like initial amounts. So we're going to try some of these. We're going to see what we can work with, see how we can use all the things we've already learned, and we're going to try some examples. So I'm going to have you try example 2 and 3. They're 2 different types. Example 2 says a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when time equals 0. So imagine the hot cup of coffee. You walk into a somewhat chilly room, you have your coffee. The coffee's temperature is changing at a rate of R of t equals -7 times 0.9 to the t degrees Celsius per minute with t in minutes. We want to estimate the coffee's temperature when t equals 10. So here, we're looking for the coffee's temperature at time equals 10. So we need to think about how that initial value plays in and how we would set this up. For example 3, we have a figure below. It shows the rate of change of the quantity of water in a water tower in liters per day during the month of April. If the tower had 12,000 liters of water in it on April 1st, estimate the quantity of water in the tower on April 30th. So again, we're approximating the area now with a graph, and we're using the fact that we started with 12,000 liters. So as a reminder, area underneath the graph needs to be counted as negative, and area above the x-axis has to be counted as positive. So try to do an estimate there. It's not going to be perfect, right? Because we don't have nice shapes, but we can do a good approximation. So I want you to try these 2 problems. Try to set them both up using the fundamental theorem. If you can, think about what your bounds are. Think about what these values would be. I'm going to give you about 4 to 5 minutes to do these 2 problems, and then we'll go through them together. I'm also going to see if I can raise these up a little so they're a little bit bigger. Let's see. There we go. Take about 30 more seconds. All right, so let's start with example 2. Need a little space here, so I have an extra piece of paper. So we know the rate at which the temperature is changing. And so typically, if you can figure out the rate, then it's a little bit easier to set up your whole equation here. So we're interested in what's happening over a 10-minute time span. So from time equals 0 to time equals 10, we're going to integrate our rate, -7, 0.9 to the t, dt. And the fundamental theorem says that that's going to be the original function at 10 minus the original function at 0. So we need to figure out how we want to represent the original function here. So the rate, right, the derivative is little r of t. So typically when we're going in this direction and we have a lowercase letter to represent the rate, we use an uppercase letter to represent the original function in order to distinguish between the original and the derivative. So here I'm going to use capital R, but if you used like Y or anything like that, that's totally fine. So R of 10 minus R of 0. So getting everything set up is sort of the biggest part of the challenge, and then we can look piece by piece to figure out what we need to solve for and what we're looking to understand in the end. So here we want to know the coffee's temperature at time equals 10. So ultimately, we are trying to solve for R of 10. So what we can do is we can add R of 0 over to the other side. So we have R of 0 plus the integral from 0 to 10, -7, 0.9 to the t, dt. So all I did is I added this term way over to the other side of our equation. Okay, so the question is, do we know these values on the left, right? Well, this integral is something that we would do on our calculator. Whenever you have an integral that has bounds, we can plug it into the calculator if there's a function here, and it will tell us the total change. So if we were to plug that into the calculator, it looks like we are going to get -43.27 degrees. Is how much the temperature changes. So the other question is, do we know R of 0, which is the initial temperature of the coffee, right? Because remember, capital R represents the temperature. So there's two different values here. We have 90 degrees Celsius and 20 degrees Celsius. And so we have to figure out which one is the temperature of the coffee. So here it's the 90 degrees. It turns out that that 20 degrees doesn't do anything for us. And so if we want to solve for the temperature of the coffee at time 10, which is over here, we're going to do 90 plus -43.27. So here, if we add those together, we get that R of 10 equals 46.73 degrees Celsius. So we had our starting temperature of 90 degrees. We figured out how much the temperature changed over that 10 minutes. And then we were able to determine the temperature at time equals 10. So that's what that would look like, set up with a fundamental theorem, isolating what we're solving for, filling in values for everything we know, and then solving for what we're looking for. Okay, so that's how we would do this algebraically. Let's take a look at the next example, which has a graph for us. So example 3 says the figure below shows the rate of change of the quantity of water in a water tower in liters per day. During the month of April, the tower has 12,000 liters of water on April 1st. We're estimating the quantity of water on April 30th, right? So the integral, if we were going to set this up as the fundamental theorem, we're looking over 30 days, right? We are integrating our function. So here we don't have an actual function that we're looking for. So we can call this little f of t dt. And we know that that's going to tell us the original function at 30 minus the original function at 0. Okay, so what I'm doing, since I don't actually have the function, is I'm just using little f of t to talk about that function. You can use little f of x, you can use f prime of x, you can use notation, but the idea is that we are trying to figure out how much water changes over this 30-day period. Okay, so again, what are we trying to solve for? We want to know how much water there is on day 30. Right? That's capital F of 30. That's the quantity of water after 30 days. So again, we can add this over. So we have F of 0 plus the integral from 0 to 30, little f of t dt equals F of 30. And so when we talk about what this means the amount of water that there is on day 30 is the amount of water that there was on day 0 plus the amount that the water changes, which should make sense, okay? Well, F of 0 is how much water there is on day 0. So that's when we start measuring. That's April 1st, right? And so we know that that is 12,000 liters, right? That's how much we start with. Then we have to figure out how much we change over these 30 days. Now, in the last problem, we were able to plug this into a calculator. On this problem, this is where we need to go to the graph to estimate the area under the curve. So when I come to the graph, right, I got to remember that anything below the x-axis is going to be negative. And so I'm trying to approximate the area sort of based on these boxes, right, and shapes that I know. So your approximation might not be exactly the same as mine, but it should be in the same general area, which I'll talk about once we get some numbers in here. Okay, so the way that I looked at this is I said, okay, this looks pretty triangular to me. So if I turn this little piece into a triangle, I can approximate the area under the curve by doing 1/2 base times height. Well, the base is 12 units long because this goes from 0 to 12. And then my height is -50. So we're counting by 50s in either direction. Okay, so I have 1/2 times 12 times -50. And so that's going to give me -300 for my approximation for the area under the curve. Again, you may have done it slightly different, which is fine, right? It's just a matter of how you set it up, but it should be somewhere in like the -200 to -500 range, right? You shouldn't be getting like -25,000, right? Something in the hundreds. So when I look at the upper piece of this approximation, it's not quite as triangular to me. So I'm going to try to count boxes, I think. So when I do that method, what I'm doing is I'm looking at the area of one box. Okay, so on this picture, each box is a 6 by 50, which is approximately 300 per box, right? And so here I have 1, 2, 3, I'm going to call this 4 full-ish boxes. And then if I pair like this part with this part, that's like a 5th box to me. And then I still have, I'm going to use another color so you can kind of see how I'm doing this. This part, and this part probably make another box. So like 6 boxes is what I'm counting here roughly, right, for area under the curve. And so remember, each box is going to be 300, which means that this upper area for me, I'm going to do 6 times 300 is going to be approximately 1,800. And so again, you may have done it slightly differently. Maybe you put in some triangles and rectangles, but your approximation should be roughly between 1,500 and 2,000, right? That should be sort of the range that you're getting. So Remember, when we talk about area under the curve, we're talking about cumulative area. So we have positive 1,800, but we have negative 300. And so we have to add those together, and that's going to give us 1,500 as the total change, because the amount of water was decreasing, but then it was increasing, and the net change was this 1,500. So this is from the graph. And my approximation is 1,500. Obviously, if you got slightly different numbers than me, then this number will be slightly different for you. So now I need to add these together. So I get 12,000 plus 1,500. So I get 13,500 as the number of liters of water after 30 days. And to me, this makes sense because I started with 12,000 and I can see that I added more area than I subtracted. So I'm expecting something slightly bigger than 12,000 as my answer. So that's how I would approach that type of graph. Now, this type of graph is more sort of fluid. And so it is an approximation, right? Sometimes we have graphs that have pretty straight lines where we can get much more accurate shapes to work with, but this one is pretty curvy, so we just have to do our best, okay? But we're gonna look at some more examples of graphs that maybe have more structured shapes we can look at next. Okay, so oh, the top of this got cut off. It says the graph of f prime of x is given below. Okay, so graph of f prime of x is given below. So this is the graph of a derivative. And we are given the information that f of 0 equals 2. Now, f of 0 is different than f prime of 0, right? So what we're saying here is that the original function at 0 has a value of 2. And this is the derivative, right? So these are different things. We want to use this information with the graph above to fill in the following table for values of f of x. Be sure to justify how you got your results. So we'll do the first part together, and then I'm going to have you try this. So we know that the value of the original function is 2 when x equals 0. So what we can do is we can think about the fundamental theorem of calculus and how that might help us get to these next points. So if we were to integrate from 0 to 1, so 1 is the next value that we're interested in, right, of our derivative, the fundamental theorem says that that will be the original function at 1 minus the original function at 0, okay? So again, we sort of have these three pieces where f of 1 is the piece that we are really interested in. So we can add f of 0 to the other side. So f of 0 plus the integral from 0 to 1 of f prime of x dx equals f of 1. So if we want to get f of 1, we need to take f of 0, which we were given, that's 2, plus the change, which is represented by the area under the curve. So we would go to our graph, we would go to 1, and we would figure out how much it changes. Well, from 0 to 1, we have a triangle. So that's going to be, again, 1/2 base times height. My base goes from 0 to 1, so that's 1 unit long. My height is -1, because we are talking about integrals here. So I have -1 times 1 times half, which is going to give me -0.5. So I have -0.5 is my area from 0 to 1. So 2 plus -0.5 means that my value at 1, f of 1, is going to be 1.5. Okay, so now I have to do this for each additional value. I have to take the amount of area I have, 1.5, and then figure out how much I change to go from 1 to 2. Then I take that value, figure out how much I change to go from 2 to 3, so on and so forth, filling in the table as I go. So I'm going to give you about 2 to 3 minutes. I want you to try to fill in all these values Again, using this area and setting up with the fundamental theorem, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we can kind of see from this example that we did together that for each of the new values, when we set it up, we're going to be bringing over the previous value to figure out what that's going to be. So to find the value of f of 2, which is the next one we're looking for, we're going to need the value of f of 1 plus the change from 1 to 2, right? Because I added this over to the other side from the fundamental theorem. So f of 1 is the value we had before, which is 1.5. And then the change from 1 to 2. So again, we're going to come over here. We're going to look at how much we changed. We see this little rectangle over here. So we're going to do base times height. So my base is 1 unit and my height is -1. So 1 times -1 is -1. So we have 1.5 plus -1, which means that f of 2 is going to equal 0.5. Because again, we're subtracting 1 from what we had. So 0.5. Now we want to find the value at 3. So again, to find the value at 3, we're going to take the value at 2 and add on the change, right? So the value at 2 we said was 0.5. And then the change from 2 to 3, again, we come up over here from 2 to 3. We have another rectangle. The base is 1, the height is -1. So we have, again, this value of -1. So we have 0.5 plus -1, which means f of 3 is going to be -0.5. Okay. And now we want to figure out what's going on at 4. So for 4, we're going to have f of 3, the value we had before, plus how much we changed. So f of 3 was -0.5. And now the change from 3 to 4, we come up here and we see that we again have a triangle, right? So 1/2 base times height. The base is 1, the height is -1. So that is -0.5. So -0.5 plus -0.5 is going to give me a value of -1. To find the value for 5, well, we're going to run out of space here. Okay, let's see. To find the value for 5, we have f of 4, which was the previous value of -1, plus the amount that we changed from 4 to 5. So up here from 4 to 5, we can kind of see that now we are back above the x-axis. And so 1/2 base times height, the base is still going to be 1, but now the height is +1. So now we're going to have +1/2 for our change. So that's way down here. So -1 plus +1/2, that's going to give us -0.5 for our value of f of 5. And then since I'm running out of space, we'll do 6 over here. So to find f of 6, we're going to have f of 5 plus the integral from 5 to 6 of our derivative here. So f of 5 was the value we had before, so -0.5 plus how much are we going to change from 5 to 6? Well, this is going to be a rectangle here. Base is 1, height is 1, so we're changing by 1. So -0.5 plus 1 gives us a value for f of 6 of +0.5. Okay, so again, what's happening here is we are using the change, right? The area under the curve to tell us how much the original function changes. So these are values on the original function, and this is the derivative function. So we could now sketch off a graph of the original function if we wanted to based on these values. But again, this function and this function, these are different but related. Okay, so that's how we use the fundamental theorem to find values of the original function. We can only find values if we have an initial value. So here we were given that f of 0 equals 2. If you don't have an initial value, then you can't figure out these values because we only know how to figure out how much the function changes. So if we don't have something to add that to start with, we only know how much the function changes and not where it actually is. Okay, so let's look at one more example with graphing. We're going to try to see what we can tie together here on a whole lot of different things. So here we have the velocity of a moving object is given in the graph below. So you can assume that anything above is going to be sort of going forward, anything below will be going backward, right? Because we have position. And so there's a whole set of questions here. The first one is just to describe the motion over the first 10 seconds. So essentially, when is it going forward? When is it going backwards? Then we talk about acceleration. Then when are we accelerating and decelerating? When are we constant? And then suppose that a time equals 0, we're at home base. How far away are we? So that means we're starting at 0. How much did we change? Okay, so as a reminder of the relationships that we need to use in this sort of scenario, S of t, right, is position. If you were to take the derivative of position, you would get v of t, which is velocity. And if you were to take the second derivative of position, which is the first derivative of velocity, you would get acceleration. Okay, so I want you to just think about this, see what you can figure out. Some of the questions, especially, B and C, are going back, thinking about the relationship between this function and the derivative of this function, even though this is already a derivative. And part D is talking about using area under the curve. Okay, so I want you to take about 3 to 4 minutes, see what you can figure out here. You can see like this is the 5, 10, 15, 20. This goes up to +5. This is down here at -5. So hopefully you can see the marks on the graph. Okay, so try that out and then we will go through it together. Okay, take about 30 more seconds. All right, so we'll just go A, B, C, D and see how we might answer these. So part A is to describe the motion during the first 10 seconds. Okay, so 10 is here. And when we talk about the motion, right, the only really way we can talk about this is when it's moving forward and back, where we said forward is positive and back is negative. And so we see that right here, at time equals 4 is when we change which way we're going. So from t equals 0 to t equals 4, we go forward. And from t equals 4 to t equals 10, we go backward. Okay, so again, where the area is going to tell us which direction we're moving, where one direction is forward and one direction is backward. We could go so far as to calculate how far we go, and we will look at that in a minute anyway. For part D, we're going to look at, how far do we go for time 4. So I won't do it in this step, but we will look at it in time D. And if we want to be more specific, we could calculate the exact amount that we go forward and amount backward. Okay, so we can add that after we calculate it in a few minutes. So for part B, it says, what is the acceleration of the object during the first 8 seconds? So acceleration is the derivative of velocity. And this is our velocity function, right? And so if we have the velocity function and we want to talk about the acceleration, we need to figure out how to talk about the derivative of this particular function. So here, we're talking about the rate of change during the first 8 seconds, which is this line here. And so we know that if our function is linear, that the derivative or the rate of change is the slope of the line. So here we want to find the slope of this line because that will tell us the acceleration, since that is the derivative of velocity. So to find the slope of this line, we can pick any 2 points on this line. So 0, 4 is this point up here. And then this one looks easier, so I'm going to do 4, 0 for my second point right here. You can pick any point on this line. I'm just picking points that I think will be easier. And again, we're looking for the slope of the line because the slope of the line is the derivative of the function. So change in y is going to be 4 minus 0 over change in x, 0 minus 4, which is going to give us -1. So during the first 8 seconds, right, the acceleration is -1. Okay, so what that tells me is I'm decelerating since my second derivative is negative, so I'm slowing down in some way. Okay, so for part C, during which times is the car accelerating, decelerating, and constant speed? So now we're trying to figure out when the second derivative, acceleration, will be positive, negative, or constant. And so we said, hey, this is going to be negative, right? Because here we are decreasing from left to right. So we are going to be decelerating whenever our function is decreasing. And so that happens from time equals 0 to time equals 8. We're going to be constant whenever our function is not increasing or decreasing, so when we're sort of flat. So we see starting at 8, that starts to happen here. Let's see, 10, 11, 12. So from time 8 to time 12, we are constant. And then we see it happens again over here. So from time 16 to time 20. And then finally, again, we see it happens a third time that we flatten out from time equals 24 to time equals 30. So all those places where we have flattened out, our second derivative would be 0, which means that our acceleration would be constant. And then we're going to be accelerating whenever our derivative is positive. So we'll do that in another color just to keep it straight. Okay. Okay, so we're going to be accelerating from 12 to 16. And again, from 20 to 24. okay? So that is sort of a connection back to the work we were doing in chapters 2 and 4. It was a little bit tricky. Hopefully you were able to kind of think about that, even if you weren't able to calculate everything out. So for part D now, says suppose that at time equals 0, the object is at home base. How far away from home base is the object at time equals 4 and time equals 12? So let's start with time equals 4. So for time equals 4, I'm going to write this up over here because I don't have a whole lot of space. I'm looking for the area under the curve from 0 to 4, because that's going to tell me how much my position changes from home base. So here for time equals 4, I'm going to do 1/2 base times height, because this is a triangle. My base is 4 units long, and my height is 4 units high. Okay, so I have 1/2 times 4 times 4, which is going to give me 8. So here I'm going to be 8. And I don't think you can see this, but the units are in meters. The units are written very lightly over here. It's meters per second. So this is going to be 8 meters from home. Okay. And then for time equals 12, I need to figure out how much my position changed between 0 and 12. Well, I've already figured out the part that's above the x-axis, but now I have to figure out all this area down here. And so 12 is here. So I'm going to break this up into a triangle and a rectangle. So my triangle here, if I do 1/2 base times height, I can see that my base goes from 4 to 8. So that's 4. And then my height, we have -4. So that's going to give me -8 for that triangle. And then for the rectangle, I go from 8 to 12. So I have a base of 4, and then it comes down to 4. So I have a 4 by 4. So that area is -16. So I have +8 plus -8, which is 0, plus -16. So I am -16 meters away from my base. Now, what does it mean to be -16 meters? It means that we are 16 meters in the opposite direction. So let me see if I can draw a picture. Say this is our base. We went 8 meters in the positive direction, but then we turned around. We came way back here, right? So we went -8 meters first. That was this -8, but then another 16 meters past the base. So that's what that means. That negative sign gives us a direction. Okay, so look and notice the differences in how the questions are worded and what we're actually looking to find, so that you can start to think about how this might be presented in a various sort of ways on homework as you try this out later today. Okay, so that is that one. The last sort of part of fundamental theorem is we often take the fundamental theorem and work with it in sort of an economic sort of business context. So we're just going to look at a couple quick examples of how this comes up in application to business. So typically the way this is going to come up is with marginal cost using the fundamental theorem, because it has relation to fixed costs, which is something we've talked about before. So remember, fixed cost is the cost when you've made no products. So if we were to apply the fundamental theorem sort of directly, we would set it up like this: A to B, C prime of Q dQ. So if we integrate the marginal cost between 2 points, A and B, it would be the cost at B minus the cost at A. Typically, we are considering what happens when A equals 0. So to make 300 products would be from 0 to 300. To make 700 products, 0 to 700. So A is almost always 0. And so the way that that impacts the fundamental theorem, right, is that we end up with C of 0 instead of C of A, and C of 0 is our fixed cost, which we've talked about before. So if we want to solve for the total cost, which is typically what we're looking for, the total cost, we would be adding this over like we were doing before, would be the fixed cost plus the change in cost. Okay, so this is very similar to what we were just doing, right? Only now we're using cost functions instead of general algebraic functions. Okay, so let's look at some examples and see how this comes up. So here, we're going to have a graph of the marginal cost of some product. Okay, so what we want to do is A, we want to set up an integral to represent the total cost to produce 150 items. Part B, we're going to use the graph to estimate the total cost to produce 150 items. Part C, we're going to now assume there's an additional fixed cost of $1,000 to produce this item. So for parts A and B, we're assuming fixed costs are 0. And so for part C, we're saying, okay, well, what if the fixed costs are now 1,000? What is the new price or the new cost? Part D, we're now going to sell these items. So for part D, we're writing a revenue function. So think back to what we know about revenue functions. And then for part E, we're going to look for profit earned by making and selling 150 of these items. So for parts A through C, we are really working with the cost function. And then for parts D and E, we're taking our answer from part C and using it with D and E to answer all those questions. Okay, so again, you can see that this function is pretty curved. So, you're just approximating the area under the curve, but I did, the solid line is where the 2 is, and then 4, 6, 8, 10, 12, 14, 16 up this axis, then 50, 100, 150, 200, 250. But again, in this particular problem, we're really only interested in what's going on until 150. So do your best to approximate. You can certainly see that you could fit in some triangles and rectangles here if you wanted to, or you can count boxes, however you want to approach it, that's fine. But I want you to take about 3 to 4 minutes, see if you can answer these questions, and then we will go through it together. Okay, take about 30 more seconds. Okay, so for part A, we just want to set up an integral to represent the total cost to produce 150 items. And so from our fundamental theorem, we would have fixed costs plus the cost from 0 to 150 of the change in cost based on the marginal cost would give us the cost to produce 150 items. So this is sort of the generic setup of the integral without plugging in any of the numbers quite yet. For part B, we want to use the graph to estimate the total cost to produce 150 items. So here is where we need to start doing some of the approximations. And again, you may have decided to approximate slightly differently than me. That's okay, but our numbers should be in the same ballpark, right? So what I did is I drew in a rectangle here for the first part. And so my rectangle had a height of 6 and a width of 150. And so that gave me an area of 900 for this box. And then I decided to approximate with a roughly triangle here, right? Realizing that I have a little bit extra here, but that seemed like the easiest way to calculate for me. And so this triangle, when I was doing the area, I did 1/2 base times height, but I want you to notice that the way I set up my triangle is that my base really only goes to 100 because I had a little tiny extra area here. So I already counted that. I didn't want to sort of double count the extra area. So my base is 100. And then my height, so remember this was 6. So this is 10, 12, 14, 16. So my height here goes from 6 to 15. So that's going to be 9, which gives me an area here, approximation of 450. So again, you may have approximated slightly differently, but your total should be in the same general area as mine. So if I add up my 900 plus 1450, I get 1350. Okay, so if you got something between, say, 1100 and 1500, then we're probably in the same ballpark. But if you're getting like 17,000, then something has gone awry. Okay, so here I'm assuming that there is no fixed cost, so this would be 0, and then the area under the curve was 1350, so my total cost is 1350. For part C, says suppose that now there is an additional fixed cost of $1,000. What is the new cost? So that means that this value, instead of being 0, is going to be 1,000. So I have to add 1,000 to my old approximation. And now I have 2,350. So as the fixed cost change, we're adding the amount of change we got from the graph plus the fixed amount to get this new amount. For part D, it says, suppose that you can sell this item for $25. Write an equation to represent the revenue function and find the total revenue for selling 150 items. So remember, revenue is price times quantity. And here we're told that we're selling them for $25 each. So that's the price. So my revenue function is 25Q. Now I want to know the total revenue for selling 150 items. So I would do 25 times 150. and that is going to give me $3,750 in revenue. Okay. And then part E says find the total profit earned by making and selling 150 of this item. So as a reminder, profit is revenue minus cost. So we calculated the revenue in part D, which is 3,750. The cost we get from part C, 2,350, and we subtract them to get our profit, which is going to be $1,400. So if we make and sell 150 of our product, our profit will be $1,400. So that's one of the ways that we can use this to sort of use the fundamental theorem to think about total cost. There's a couple of other different ways that this comes up. So we won't have time to go through both examples. So instead, I'm just going to talk about how we would do these examples so you can try them on your own. So for example 7, the total cost in dollars to produce Q units of a product is given by this down here, marginal cost, and we have a fixed cost of 20,000. We want to approximate the total cost to produce 150 items. So we would integrate our rate from 0 to 150. And then we would add to that 20,000 because we'd have to add on the fixed costs. Okay, so that's what we do for part A. That's what we've been doing. But part B and C are a little bit different. So for part B, it says to find the value of C prime of 150 and interpret your answer in terms of cost production. So to get the marginal cost at 150, we would literally plug 150 into the marginal cost function. So we plug it into the Q squared, we plug it into the Q. When you compute that, you would get something like 20.01, I think, is what you would get when you plug it in. And what that means is it's the additional cost to produce one more item. So the number you get here is the additional cost to go from 150 items to 151 items. So then part C wants you to estimate the cost of 151 items. So this is going to tie back to when we did local linear approximation. We know the cost at 150. We know the derivative of cost at 150. So we're able to approximate the cost at 151 by using the local linear approximation. For example 8, this one's a little tricky because we have a table of the derivative and we have fixed costs or 10,000. We want to estimate the total cost of producing 400 units. So the first thing I want to point out is that 400 is in the middle of the table. So we're not even using anything after 400. And so we have to go back to how do we approximate off the table? We would need to do a left-hand estimation. We would need to do a right-hand estimation. And then from that, get the best estimate. The best estimate would then represent the area under the curve. And to that, we would need to add on our fixed costs. So that's how we would approach example 8, okay? So example 7 and example 8 are both posted on the lecture page in Moodle. So if you want to look through them after you've tried them, you can see the final solutions there, okay? So good luck today with the end of your classes and things like that. Don't forget about your chapter quiz tomorrow, and definitely feel free to stop by, drop in help tonight or tomorrow night if you have any last minute questions.